Bases. Remember that we have two different definitions for bases. We've got our Arrhenius definition of bases, which says that a base is a substance that produces hydroxide ions in an aqueous solution. And then we've got our Bronsted-Lowry definition, which deals with what bases do during chemical reactions. And bases are substances that accept protons or hydrogen ions during chemical reactions. So let's look at a strong base problem first, and then we'll look at a couple of weak base problems. So it says calculate the pH of a solution made by putting 4.63 grams of lithium hydroxide in enough water and diluting it to a total volume of 400 milliliters. All right, so we've got a strong base. We know it's going to break up into ions in solution, and it's going to 100% dissociate. We need to calculate the concentration of the lithium hydroxide, which will be equal to the concentration of the hydroxide ions in the solution. And then from there, we can use our equations that deal with the pH scale to calculate the pH of the solution. All right, so we've got our lithium hydroxide is going to dissociate into lithium ions and hydroxide ions. Now let's calculate our concentration. So 4.63 grams of lithium hydroxide. We know from the periodic table that 1 mole of lithium hydroxide is 23.92 grams. So that'll give us 0.194 moles of lithium hydroxide. We'll divide that by the volume, 0.400 liters, and that's going to give us a concentration of 0.484 molar lithium hydroxide. And since it's a 1-to-1 ratio of lithium hydroxide to hydroxide ions, that 0.484 is the concentration of our hydroxide ions. So now we can figure out our hydrogen ion concentration. We've got 1.00 times 10 to the minus 14 equals our hydrogen ion concentration, which we don't know, times our hydroxide ion concentration, which is 0.484. Divide both sides by 0.484, and our hydrogen ion concentration will be 2.07 times 10 to the minus 14 molar. To calculate our pH then, we'll take the negative log of 2.07 times 10 to the minus 14, and we're going to get a pH of 13.7. So strong base problems are pretty straightforward. Now, let's look at weak bases. It says many types of proton acceptors, or bases, do not contain hydroxide ions, so they're a little bit harder to recognize. But when they dissolve in water, they increase the concentration of hydroxide ions because they react with the water. So if we look at an example, ammonia is a base in water. It's a proton acceptor. Now the proton that the ammonia is going to accept comes from the water molecules. So the conjugate acid of ammonia is our ammonium ion, and the conjugate base of water is hydroxide. So although ammonia doesn't have hydroxide in its formula, when it's added to water, it increases the hydroxide ion concentration. Since it's a weak base, we can write a Kb expression. We'll take the products over the reactants, but remember that liquid water is not going to be incorporated into that K expression. So Kb always refers to a reaction of a base with water to form a conjugate acid and hydroxide ions. So we're going to look at an example of a weak base solution and calculate the pH. The steps are going to be basically the same as the steps we did for weak acids, except this time when we go through our steps, we're going to be looking at the hydroxide ion concentration instead of the hydrogen ion concentration. So our problem says calculate the pH of a 0.35 molar solution of methylamine, and it gives us the Kb value. Our first step is going to be to list the major species in the solution. So we have water, which can produce hydroxide ions. And we've got the Kw value of 1.00 times 10 to the minus 14. And then we've got the methylamine. But in order for us to figure out where that hydroxide ion comes from, we're going to have to react it with water. We're going to end up with a methylamine ion and a hydroxide ion. And the production of that hydroxide ion is what makes methylamine a base. And it tells us that the Kb is 4.38 times 10 to the minus 4. So now that we've done that, we want to decide the equilibrium that's going to produce the hydroxide ions. We've got 10 to the minus 14 for water, 10 to the minus 4 for the methylamine. So the methylamine by far is going to dominate in producing hydroxide ions. And we'll write our Kb expression. So Kb will equal the concentration of the methylamine ion. That should be just a 1. Times the concentration of our hydroxide ion over the concentration of our methylamine. Next, we'll make our ice chart. So we've got our methylamine, we've got our methylamine ion, and we've got our hydroxide ion. So initially, we've got 0.350 molar methylamine, and since the dissociation hasn't taken place yet, we've got none of those ions in solution. We don't know what our change is, but we know that some of that methylamine will react with water, and it's a 1-to-1 ratio, so we'll produce X and X amount of our ions. Now we'll look at our equilibrium values. So 0.350 minus X, X, and X. Next, we'll plug our values in. So we've got 4.38 times 10 to the minus 4 for our Kb, X squared over 0.350 minus X for our equilibrium concentration of our methylamine. And again, we're going to assume that our X is insignificant to make the problem easier, and then we'll prove that by using our 5% rule. So we'll say this X is insignificant. We're going to multiply both sides by 0.350, take the square root of both sides, and that will give us our value for X. So our X value will equal 1.24 times 10 to the minus 2, and that's our concentration of our methylamine ion. It's also the concentration of the hydroxide ion, which is what we're going to need in order to calculate the pH of the solution. Now, let's prove that that X is really insignificant, so we'll do our 5% rule. We'll take 1.24 times 10 to the minus 2 divided by the original concentration, which was 0.350, multiply it by 100, and that'll give us 3.54%. That's less than 5%, so our x is insignificant, and it was okay for us to solve the easy way. Now we figured out what the hydroxide ion concentration is, but the question wants to know what the pH is. So we've got two options. We can take the hydroxide ion, take the negative log of that value, and that'll give us the pOH, subtract it from 14, and that'll give us the pH. Or we can calculate the hydrogen ion from the hydroxide ion using Kw, and then take the negative log of the hydrogen ion. Either way will give you the same answer. So I'm going to calculate the pOH of the solution first. I'll take the negative log of 1.24 times 10 to the minus 2, and that'll give me a pOH value of 1.91, and then my pH will be 14 minus that 1.91, and that'll give me a pH of 12.09. So when we solve weak base problems, we're essentially doing the same thing as when we solved weak acid problems. We're going to first list the major species, decide what the major contributor of the hydroxide ions are out of the species that are in the solution, write our reaction with water, write our Kb expression with our ice chart, plug our values in, assume that x is insignificant, solve for x the easy way, use our 5% rule to verify that x is insignificant, and then solve for our pH and anything else that we're asked for.